Okay, so welcome to our session. In this session, our main goal is to talk about exact differential equations, how do they look, and how to solve such equations, and to talk about integrating factors of some special exact differential equations. So we are going to indulge into a lot of first order differential equations in this one session. Okay, so exact differential equations. Right? Let's start. So let us start with the basic definition. Okay, so what is a differential equation to be precise? So an equation involving derivatives of one or more dependent variables with respect to a single independent variable. Rather, if I talk about a differential equation, so with respect to one or more independent variable can also be talked about. With respect to one or more independent variable is called a differential equation. It's called a differential equation. Fine. If the independent variable is one, that is, there exists only one independent variable with respect to which you are talking about an equation which involves derivatives. In that case, we say it to be an ordinary differential equation. The equation is said to be an ordinary differential equation. So an ODE involves a single independent variable. A single independent variable. Fine. We specifically want to talk about first order differential equations in this lecture, first order ordinary differential equations in this lecture. And precisely our main concern would be linear differential equations. So an nth order linear differential equation is given in this form. So it's of the form a n x dny over dx to the power n, which is the nth derivative of the function of the independent variable y with respect to the of the dependent variable y with respect to the independent variable x. Okay, so y is basically a function which depends on x, right? Plus n minus 1 of x dn minus y dx to the power n minus 1, and it continues till a1x dy over dx plus a0y to be equals to some function dx. Okay, so this is called a linear differential equation where each of these functions a and n minus 1 are all functions of x. The right hand side also involves the function of x, and the function a n is not identically 0. That is, the function which is the leading coefficient of this differential equation, that is not identically 0. Fine. So this is called a nth order linear differential equation. But order specifically, it corresponds to the highest order of the differential present in this equation. Fine. Now our concern, as I said, is on first order differential equation. So our concern is first order, rather linear differential equations. Fine. So what are the specific forms of first order linear differential equation might take? So you have this most standard form, which is the derivative being a function of x and y, which can be equivalently represented as in this form. So m dx, or rather more precisely, a function of xy, which we denote as m, times the differential dx plus a function of xy times the differential dy is equals to 0. Okay, this is also another form. So this is not, this is sometimes called the non-trivial form, right? And these two forms are interchangeable, right? For example, you might have, let's say, let's say dy over dx to be is equals to x square plus y square, some sort of like this, then you can represent this as dx square plus y square times dx minus dy is equals to 0. And similarly, if you have some form like this, you can re-interchange it to the standard form. This is called the standard form. Clear? Okay. Yeah. Right. Clear? Okay. Now let us involve a definition. Okay. So if f is a function of two real variables and its first partial derivatives are continuous, first partial derivative, that is del f upon del y and del f upon del x, are continuous. So the first partial derivatives are continuous. Sometimes we will be directly denoting it to be a C1 function. Clear? In some domain D. So a domain can be thought of as an open connected region or an open convex region. Okay, so you need it to be open, and in general you need it to be connected, or rather simply convex. Fine. Okay. So in a domain D, then we define the total differential of f as, so we write it as d of f at xy to be the partial derivative with respect to x times dx plus the partial derivative at xy with respect to y dy. Okay, so this is called the total differential of f. Fine. Example, let's say f of xy is xy squared plus 2x cubed y. Then in this case you will write the df to be the partial derivative with respect to x. So it's y squared plus 6x square y dx plus, this is 2xy plus 2x cube dy. Fine. So this gives you the total differential. Yeah. Right. Now, suppose you are given a linear first order differential equation, or rather you do not talk about linearity for now. Let's just leave the notion of linearity for now. Let's just talk about a first order differential equation. Okay. Suppose dy by dx is equals to function of xy is a first order ODE, first order ordinary differential equation. So we can write that equivalently in the form, right? M dx plus n dy is equals to 0. Right? This is one way of writing it down. This should be n. Yeah. Clear? Now, so you need to keep this in mind for now. Okay, because we are going to define the notion of a first order ordinary differential equation being exact in terms of such an equation. Now, given two functions m and n on R2, that is functions of two real variables, we say mxy dx plus nxy dy to be exact differentiable, in a region or a domain D if there exists a C1 function f on R2 such that the total derivative of f at xy is basically m dx plus n dy. Clear? That is, if there exists a C1 function f on R2 such that its partial derivative with respect to x is m and its partial derivative with respect to y is n, right? So given two variable real valued functions, two real variable functions m and n, this expression m dx plus n dy is said to be exact differentiable if there exists a C1 function which is also a two real variable function such that the total differential of that function, it is exactly equal to the expression m dx plus n dy. In other words, if the partial derivative of f with respect to x is m and the partial derivative of f with respect to y is n, right? Now let this expression be a. Okay, we will be referring to this expression over and over again. Okay, so let me change the page. Now suppose m dx, where m and n are again two variable functions. I'm not repeating that anymore. So let m dx plus n dy equal to 0. Uh, you know that this is exact, or rather exact differentiable as per our definition, right? Then we know that there exists a C1 function such that this is the total differential of it. And in that case, we have d of f xy to be 0, right? By definition for some C1 function, right? Fine. Therefore, this solving this differential equation is just solving this differential equation, and this will give you a function f equals to some constant c, right? If you integrate it on both sides, you will get a function f which is of two variables. On the right hand side you will get a constant, and this will give you the solution 2a, right? You will get the solution of the differential equation of the form c. Fine. And we will see that this is somewhat one of the most important sort of a differential equation, first order differential equation which exists. And such equations are called exact differential equations. So definition, an ODE m dx plus n dy equal to 0 is said to be exact if the expression m dx plus n dy is exact differentiable. Is exact differential. Clear? That is the notion of a exact differential equation. And now we will be observing some properties these exact differentiable equations some of the properties which these exact differential equations possess. Fine. Now observe the first important property. Observe that if m dx plus n dy is equals to 0 is exact, right? Then there exists a C1 function, right? F such that del f by del x is equals to m and del f by del y is equals to n, right? So if I partially differentiate each of these expressions again with respect to the other variable, because f is f has independent variable x and y both, so I can partially differentiate it with respect to x and then with respect to y, or vice versa, first with respect to y and then with respect to x, right? So this implies that if I del to f by del y del x, which is just del over del y, that is partially differentiating del f over del x with respect to y, this is just del m by del y. And similarly, del to f by del x del y is equals to del over del x of the partial differentiation with respect to y of f, which is just del n by del y. Sorry, del n by del x. Fine. Now there is a very important property of mixed partial derivatives, is that if the function is a C1 function, that is its first partial derivatives are continuous, then the mixed partial derivatives are interchangeable. So since f is a C1 function, therefore del to f by del x del y at any point is equals to del to f over del y del x, which implies that del m by del y is equals to del n by del x. And that is one of the most interesting properties of the exact differential equations, which if you have studied differential equation, you studied this somewhere somehow, that to check whether a differential equation is exact, you need to check exactly this property. That is, you first convert it into the non-trivial form and then you check this property. Okay, so this is checking exactness. Okay, fine. But sort of a converse of this statement is true as well, right? Oh, before first let us encounter an example. Example: consider y squared dx plus 2xy dy to be equal to 0. Is it exact? Yeah, so we can directly check it from here, right? So let m be equals to y square, n be equals to 2xy. Then this implies that del m by del y is equals to 2y and del n by del x is also equals to 2y, right? And therefore this expression is exact. Now there's a problem here because we have proved that if the equation is exact, then these conditions hold, but we have not yet proved the converse of this statement, right? So checking right in this way is not exact at this point. Okay, so let us prove that this equation is exact in a more fundamental way through the definition, right? So I have m to be of this form and I have n to be of that form. N is equal to 2xy and m is equals to y square. Now if I choose f to be, let's say, xy square, then clearly it's a C1 function. Clearly it's a C1 function. And observe that del f by del x is m, del f by del y is 2xy, which is n. And therefore it's a exact differential equation. Now, proving it in this way is there, right? Because we have studied it in terms of the definition itself, that there is the exactly definition of exactness of a differential equation. Yeah, so proving it in this way is obvious, but to prove that a differential equation is not exact with the tools we have right now, we can easily check whether this is true or not, right? For example, if I take this equation, let's say y dx plus 2x dy to be equal to 0, then you will observe that del m by del y is 1, which is not equals to del n by del x, which is basically 2, right? Because this property is not holding, therefore it cannot be exact, right? So therefore this differential equation is not an exact differential equation. But now we prove, so this is a theorem that, okay, if del m by del y is equals to del n by del x on the domain we are concerned about, domain D, then the equation m dx plus n dy equal to 0 is an exact differential equation. Fine. And this we are denoted as a, so we will keep denoting it as a itself. Fine. Right. Let us move forward. So we'll try to prove this, and the proof is, I won't say it's complicated, but it's sort of a constructive proof. So the proof is a sort of a constructive proof. So we will construct out the function which will act as f, whose partial derivatives are m and n respectively. Fine. So let us move on to the next page. So proof. Okay. So what I need to show is that, to show that there exists a C1 function f such that del f by del x is equals to m and del f by del y is equals to n when m dx plus n dy equal to 0 is such that del m by del y is equals to del n by del x. Fine. We directly need to prove this. Okay. Now, suppose I consider this to be true, which I can surely do. I can get hold of such a function such that it satisfies only this much of the equation, and using that we will try and construct out, or rather modify the function in such a way that it also satisfies this property. Rightly talking about a function which directly satisfies both of these properties is not possible at this point, but we can rightly talk about a function which satisfies one of the properties. Okay, so let f be a function such that f can be written as the integration of mxy partially with respect to x, and in that case I will have a constant of the integration which should be a function independent of x and purely a function of y. Fine. Right. So by an integration partially with respect to x, what do we mean is that in this integration y is constant. Y is here to be constant. The only function on which this integration is depending is on the variable is x. Fine. So I have such a function f, right, which satisfy one of those equations. Now observe that del f by del y is del y of the integration mxy del x plus now partially differentiating phi with respect to y same as totally differentiating it. So this is fine. Okay. Now we want that del f by del y to be equals to n, right? Then to have that I need to have d phi by dy to be equals to nxy minus del over del y integration of m xy dy. Sorry, mxy del x. Sorry, del x. Right. Now what do we have? Now phi is independent of x. Right. Phi is independent of x. Therefore, so is its derivative with respect to y. Right. Therefore, so is its derivative with respect to y. Now, if the left hand side of this equation is independent of x, so the right hand side must also be independent of x. For the right hand side to be independent of x, its partial derivative with respect to x must be 0, right? Therefore, we need to show that del by del x of nxy minus del y of m xy del x, this is 0, right? This is what we need to show. Okay, suppose this is 1. Okay. Now observe that yeah, so I need to come up and show this. Now given that del f by del x is equals to m, del f by del y is equals to n, is something rather, given that, okay, I wrote a wrong hypothesis. Now given that del m by del y is equals to del n by del x, and we want to show that del f by del x is equals to m and del f by del y is equals to n. Now observe that what is so now what is del f by del x? That's what I mean. Okay, now del f by del x equals to m. This means that del 2 by del x del y integration of mxy del x plus del x del by del x of phi y is equals to m, right? Sorry, is equals to, extremely sorry, is equals to, so I'm differentiating f with respect to x, fine, and this is equals to m typically, right? Getting my point? Because we have structured f to be of this form, right? Yeah. So what do we conclude up from here, right? That is what I want to talk now. Okay, now no, this is not equals to m immediately. Okay, wait a minute. I need to show this up, right? I need to show that del f by del x equal to m and del f by del y is equals to n, right? Okay, now for this to hold true, given del m by del y is equals to del n by del x, that is something which is given to us, rather we do not require that right at this point. But for this to hold true, observe that del 2 by del x del y times the integration of mxy del x must be equals to del 2f by del x del y, but that is exactly equals to del 2f by del y del x by continuity, which is equals to del 2 by del y del x integration of m of xy del x. Yeah, that is something we require. Fine. Now I got it. I got a bit confused because I just wrote out that we want to show this, and therefore I could not have concluded what I had written. Yeah, so I need to write it. I get this conclusion because I need to have this to be true, right? In order to have such a function which satisfies the property which we require. Fine. Now once we have this, therefore del by del x of nxy minus del by del y integration of mxy del x, this is equals to del n by del x, right, minus del 2 by del y del x, sorry, del 2 by del x del y integration of mxy del x. But then I can interchange it right from here, right? I can interchange the del x del y. So this is equals to del n by del x minus del 2 by del y del x of integration mxy del x. But integrating mxy del x, integration of mxy del x, and then differentiating with respect to del x itself will give you m. And then you have the derivative, partial derivative with respect to y, right? So this is equal to del n by del x minus del m by del y. And since you are given that del n by del x equal to del m by del y, it is equal to 0. It is equal to 0 on D. Fine. Let's wait a minute. Yeah. This implies that d phi by dy is independent of x. Fine. And once it is independent of x, I can talk about phi y. This implies that phi y is equals to integration of nxy minus integration of del m by del y del x dy. Fine. And once we get hold of phi y, then recall how had we structured f. Therefore f of xy, which was given to be integration of mxy del x plus phi y. So this is just integration of mxy del x plus so the phi structure of phi y was integration of nxy minus integration of del m by del y del x whole in terms of dy. And this gives you the structure of f. And f immediately obeys all the properties of the of the function which we require to show that the differential equation m dx plus m dy is equals to 0, because we have just constructed f in such a way that it satisfies all those properties. Fine. So there's nothing to check anymore, and this gives you the end of the proof. Right. Now we give a way to solve a differential equation, exact differential equation. Okay. So solving an exact differential equation. Okay. So suppose you are given this equation, let's say 2x sine y plus y cube e to the power x dx plus x cube cos y plus 3y square e to the power x dy is equals to 0. I want to check whether firstly I want to check whether it is exact or not, and then I will try to solve this exact differential equation. Suppose m is equals to 2x sine y plus y cube e to the power x, n is equals to x cube cos y plus 3y square e to the power x. Then this implies that del m by del y is equals to 2x cos y plus 3y square e to the power x, which can immediately be seen to be del n by del x. Therefore we have an exact differential equation. Therefore this is exact. Now we need to solve this differential equation. Now recall we had said that if m dx plus n dy equal to 0 is an exact differential equation, then that corresponds to solving this differential equation. Right? So actually what do we need to solve is this differential equation. So what we actually need is to solve df in terms of del f by del x dx plus del f by del y dy. Clear? Right. That is exactly what because if I get hold of del f by del x and del f by del y, then we are good to go. Fine. So let del f by del x to be equals to m. In that case, we have f to be the integration of m partially with respect to x. So I just need to treat all the y's as constant, And in this case, since the y's are being treated as constant, the constant of integration will also be a function purely of y. So integrating m with respect to x, what do we get? Partially, we get x square sine y plus y cube e to the power x plus some function of y. And similarly, del fy del y equal to n implies that f is of the form. So let me again go back and check how n looks like. Yeah, so this should be x cube sine y plus y cube. Okay, I'm getting, yeah, fine. Wait a minute. So n was 3y square x, right? Fine. So what do we get up from here? Yeah, so y cube x, and here also I have y cube e to the power x plus psi of x, right? Here I need to get here a function purely of x, right? Therefore, our solution to this differential equation. So how do we write it? Differential equation. Just write each of the expression you have got for f one by one. If there is some repeated elements, write it only once, and that equals to a arbitrary constant c is your solution. So now you can see that both the expressions are repeating twice in both the expressions for f. So solution is just x square sine y plus y cube. I get this was x square plus y cube e to the power x is equals to constant. So that will give you the solution. Fine. Let us do another example. Example 3x square plus 4xy dx plus 2x square plus 2y dy is equals to 0. Right. So let m be 3x square plus 4xy, n be 2x square plus 2y. Then del m by del x, del m by del y is equals to 4x, and del n by del x is also equals to 4x. Therefore, this is exact, right? So as I said in the previous example, what we need to do is that we need to integrate m partially with respect to x. We need to integrate partially. We need to integrate n partially with respect to y, and then write the expression as I said in the previous example. So let f b is equals to integration of m partially with respect to x, which is just x cube plus 2x square y plus some function of y. Similarly, is to be integration of n with respect to y, which should give you 2x square y plus this should give you y square, right? Plus some function of x. Clear? Therefore, our solution is, so writing each of these terms and writing those terms only once which are being repeated, and that equals an arbitrary constant will give you the solution. So I have x cube plus 2x square y, it is being repeated, plus y square equals to c. This is your solution. So in fact, this gives you a one parameter family of solutions because there is only one arbitrary constant which deals with the gradient of the solutions, or rather that works as the parameter for the solution, right? So this gives you a one parameter family of the solutions. One parameter family of the solutions. Getting my point? Okay. Now we are intended to talk about integrating factors. Integrating factors. So what is basically an integrating factor? Suppose m dx plus n dy equal to 0 is not exact on a domain D. Now, if there exists a function mu of xy on the domain D such that mu of xy times m of xy dx plus mu of xy times m of x n of xy dy is equals to 0 is exact. So multiplying by this specific function will make the equation exact. In that case, is exact, then we say that mu is an integrating factor, because once it is exact, it is very easy to integrate it further, right? So that's why the name. So it's called an integrating factor, right? Let us quickly go to an example, and this is an example which we have already encountered. Recall that y dx plus 2x dy equal to 0 is not exact, but y times y dx plus 2x dy equals to 0. Rather, this is sort of an abuse of notation. I shouldn't write it in this way. I should write it in this way. Rather, y times y dx plus y times 2x dy equal to 0, which is equivalent to writing y squared dx plus 2xy dy equal to 0 is exact. This is also something which we had checked. Clear? Got it? Fine. So in this case, we will say that y mu of xy equals to y is the integrating factor. Clear? Got it? Okay. Now suppose we are given a function whose integrating factor is not, we are not being able to find. One of the ways to examine an integrating factor is of this form. This is just an example. Example. Consider the equation y square plus 2xy dx um, minus x square dy equals to 0. Okay. Now one of the ways to find an integrating factor is to multiply it with respect to some integral power of x or with some integral power of y, and just examining the conditions of being exact, we need to find a value for the integral power, and that will give you the integrating factor. That is the example which I am trying to do up here. So consider, so this is not exact, okay, that is something you can check on your own. This is not exact. So consider multiplying this with y to the power n. So consider y to the power n times y square plus 2xy dx minus y to the power n into x square dy to be equal to 0. We consider this equation. So on slightly simplifying, we get y to the power n plus 2 plus 2x y to the power n plus 1 dx minus x square into y to the power n dy is equals to 0. Or we can write it plus here, minus inside. Fine. Now I want to make it exact. So I need to find the integral power of y with respect to which this becomes exact. Now suppose exact. So suppose I choose this to be m, I choose this to be m. Suppose exact, then del m by del y should be equal to del n by del x. Therefore, so partially differentiating this with respect to y will give you n plus 2 times y with respect to n plus 1 plus 2 times n plus 1 x into y to the power n should be equals to minus. So what should this give you? This should give you 2 times x y to the power n. Fine. Therefore, for this to be 0, you can easily observe that you can just compare the coefficients and see that this term should be 0. This implies that n plus 2 y to the power n plus 1 should be 0. Now since y cannot be identically 0 because that makes no sense at this point, therefore n plus 2 needs to be 0 or n needs to be minus 2. Therefore the integrating factor here, is y to the power minus 2. Got it? Fine. Now we want to check some specific examples, or rather some systematic equations which admit some some specific integrating factors. Okay. Yeah. So examples. Okay. So this just so I'm just stating it in terms of a theorem. Consider the differential equation mxy dx plus nxy dy is equals to 0. Fine. Now if 1 upon nxy times del m by del y minus del n by del x, if this value is depending only on x, then the integrating factor, let this be 1, then the integrating factor for 1 is the exponential of the integration of 1 upon nxy del m by del y minus del n by del x dx. Fine. Therefore, if you are given a differential equation such that 1 upon n times del m by del y minus del n by del x, it is depending only on x, then the integrating factor for this differential equation in terms of for making it to be an exact differential equation is given by this, right? Given by this expression. Similarly, if 1 upon mxy del n by del x minus del m by del y depends only on y, then the integrating factor for 1 is given by the exponential of the integration of 1 upon m del n by del x minus del m by del y dy. Clear? Got it? Okay. Let us get an example. Okay. Example. So consider this example: 2x square plus y dx plus x square y minus x dy to be equal to 0. Right? So let the first step always is to choose m and n. So m is this, n is this. Fine. Then what is del m by del y? So it's 1. What is del n by del x? So it's 2xy minus 1. Right? Then observe that therefore okay, so what should be the integrating factor to talk about here, right? So what if I take 1 upon n and I take del m by del y minus del n by del x. So this is 1 upon n. So this is 1 upon x square y minus x, and above what do we have? So del m by del y 1 minus del n by del x. So minus 2xy plus 1, right? So this is basically 1 upon x square y minus x. This is 2 minus 2xy, right? So if I take x common from outside, so this is xy minus 1, that's x, and I have 2 here, I have 1 minus xy, right? So therefore this is equals to minus 2 upon x. Therefore this is independent of y. Therefore this is independent of y. And once it is independent of y, therefore the integrating factor, if you recall, what should it be? It should be the exponential of the integration of 1 upon n del m by del y minus del n by del x dx. Fine? Yes? Okay. Right. Let us serve us another important property of some special integrating factors, existence of some special integrating factors. Let me just add it as a remark. If m of xy dx plus nxy dy is equals to 0 is homogeneous, that is m and n are homogeneous functions of x and y is homogeneous, and mxy times x plus nxy times y is non-zero, then our integrating factor is 1 upon mxy times x plus nxy times fine. So we end this session. So what we have concluded here is what is, so let me just recall once. So we have the definition of an ODE, then we talked about exact ODEs, then we talked about the checking exactness in terms of two theorems, rather one theorem, then we talked about solving them, and we essentially talked about integrating factors. So now we end this session by giving a example of a special type of a ordinary differential equation once again, which is called the ODE in Clairaut'S form. Fine. So what is this form basically? So y is equals to px plus a function of p, where p is identically the function dy over dx, is called the Clairaut'S equation. Clear? I want to solve this equation. Okay, so let's try and solve this equation. If I differentiate with respect to x, differentiating with respect to x, what do I get? So I get dy by dx is equals to so this is dp by dx times x plus p plus f prime of p times dp by dx. Right, simple chain rule on the rightmost element. But then dy by dx is just p, dp by dx times x is as it is, plus p plus f prime of p dp by dx. So these p's cancel out. So I get what do I get? X plus f prime p times dp by dx is equals to 0. Right? So suppose x plus f prime of p is non-zero, then I have dp by dx to be equal to 0. But in this case, I get p equals to c, which is a constant, to be a solution. Therefore, putting this in the equation which we started with. So putting this in here, 1. So putting this in 1, we have, so what do we have if I put this in 1? So I get y is equals to cx plus f of c. And this gives you again a one parameter family of solutions. A one parameter family of solutions to the Clairaut'S equation. Is it clear? So this is just an exercise for the end of the session. Exercise. What will happen? What will happen? See, we have assumed here that x plus f prime p is non-zero. What will happen if it's 0? So what will happen if x plus f prime p is exactly equal to 0? Right? So try and check this out, and we'll meet soon in some other session. Thank you.